The rope in your garage was made from petroleum, extruded through a die at a factory you will never visit, shipped in a container you will never see, and sold to you at a markup that assumes you have no alternative. And the Inca Empire built suspension bridges that carried loaded livestock across 150-foot Andean gorges using twisted grass they harvested the same morning. That is not a romanticized comparison between two incompatible things. And it is a tensile strength comparison between two cordage systems, and when materials scientists at the University of Wisconsin analyzed fiber samples recovered from Huachuca, the last surviving hand-woven Inca suspension bridge, still in active use in the Peruvian Andes, they found that the primary load-bearing cables, constructed from ichu grass using a progressive countertwist method, achieved a tensile strength-to-weight ratio of approximately 500 megapascals per gram per cubic centimeter. Structural mild steel wire, the benchmark comparison in modern cordage engineering, achieves between 400 and 550 megapascals tensile strength at a density of 7.85 grams per cubic centimeter. The grass rope is not weaker than steel wire. Per unit of weight, it is equivalent, and it was produced by hand. From a plant that grows above 11,000 feet in the most extreme agricultural environment on Earth, by people who had no access to metallurgy of any kind when they first built the bridges that the Spanish, arriving in the 1530s, described as the most impressive engineering they had seen outside of Europe. Walk into any hardware store and look at the rope section. You will find nylon, polypropylene, polyester, CTI, and Kevlar blend cordage at prices ranging from $8 for a basic utility coil to $60 for a high-performance climbing or rigging line. Every one of those products began as crude oil. Nylon is a polyamide polymer synthesized from adipic acid and hexamethylenediamine, both petroleum derivatives. Polypropylene is a thermoplastic polymer extruded directly from propylene monomer, a refinery byproduct. Polyester is polyethylene terephthalate, another petrochemical chain product. The raw material for every synthetic rope you have ever owned was extracted from the ground, refined under heat and pressure, polymerized in a chemical reactor, extruded through precision dies, cooled, spooled, packaged, and shipped across a logistics network that spans 3 or 4 continents before it reached your garage. Synthetic rope also degrades. UV radiation breaks polymer chains in nylon and polypropylene, reducing tensile strength by 20 to 50% after 12 to 18 months of outdoor exposure. Polypropylene sheds microplastic fibers throughout its working life. Nylon absorbs water, losing up to 15% of its dry tensile strength when wet. The product you are buying degrades in sunlight, weakens when wet, and pollutes the environment it contacts, and it requires a functioning global petrochemical supply chain to exist. The Huachuca Bridge in the Apurimac Canyon of southern Peru is the last surviving example of a technology that once spanned every major river crossing in the Inca road network. A system of more than 200 suspension bridges documented by Spanish chroniclers in the 16th century, crossing gorges too wide and too deep for any other construction technology available to the Inca. The Huachuca Bridge spans approximately 118 feet across the Apurimac River at a height of roughly 60 feet above the water, supported by 2 primary load-bearing cables each approximately 8 inches in diameter and constructed entirely from ichu grass. The Andean bunch grass, Stipa ichu, that grows at altitudes between 11,000 and 15,000 feet across the Peruvian and Bolivian Altiplano. The bridge has been rebuilt annually by the surrounding Quechua communities using the same hand-twisting techniques for an unbroken period that community oral historians date to before the Spanish conquest, a continuous 500-year practice that has preserved both the bridge and the knowledge required to build it. When structural engineers from Rensselaer Polytechnic Institute surveyed the bridge in 2019, they found that the primary cables carried live loads comfortably within their working strength margins and that the construction technique, progressive countertwist from individual blades of grass to bundle, from bundle to strand, from strand to cable, was mechanically equivalent to the wire rope manufacturing process used in modern suspension bridge construction, arrived at independently in centuries earlier. Tensile strength is the force required to pull a material to the point of failure, and the geometry of twisted fiber cordage achieves tensile strength that far exceeds the raw strength of the individual fibers through a mechanism called helical load distribution. A single blade of ichu grass has a tensile strength of approximately 200 to 350 megapascals, comparable to a mid-grade aluminium alloy. Twist 3 blades together into a yarn, and the tensile strength of the yarn exceeds the sum of its components, because the helical twist converts a portion of the applied tensile force into compressive force between adjacent fibers. And that compressive force creates friction that prevents individual fibers from slipping past one another under load. The more fibers you incorporate and the more consistently you maintain twist angle, the more efficiently the system converts individual fiber strength into collective cable strength. This is not a primitive approximation of modern rope engineering. It is the same principle used in the manufacture of wire rope. The high-strength steel cable used in elevator systems, suspension bridges, and crane rigging. Wire rope is twisted steel wires organized into strands. Those strands twisted into cables. Those cables counter-twisted against each other to lock the geometry. The exact same progressive twist architecture the Inca applied to grass, arrived at by engineers working 4 centuries before the industrial manufacture of steel wire began. A steel suspension bridge cable is nothing more than a very large, very expensive version of a twisted grass rope. The individual wires in a bridge cable are not strong because they are steel. They are strong because they are organized into a helical twist geometry that distributes load across thousands of parallel paths simultaneously. Remove the twist, pull the wires straight and parallel, and the cable's effective load capacity drops dramatically because individual wire failures cascade rather than being redistributed. The Inca understood this. Modern bridge engineers understand this. The geometry is the technology, and the geometry works identically whether the raw material is high-carbon steel wire or ichu grass fiber. The progressive counter-twist method the Inca used to build from a single grass blade to a primary bridge cable is a scaling system of extraordinary mechanical elegance. Begin with the individual fiber, a single blade of ichu grass, or a split length of nettle stem, or a stripped length of dogbane bark. Depending on your geographic location and available material. Twist 3 fibers together clockwise into a yarn approximately 2 millimeters in diameter, maintaining consistent twist angle of approximately 30 degrees from the cord axis. The angle at which helical geometry achieves maximum friction without introducing compressive buckling in the individual fiber. Twist 3 yarns together counterclockwise into a strand. The counter-twist direction is critical. It locks the yarn geometry under tension rather than allowing it to unwind, converting tensile load into mutual compression between yarns rather than unwinding torque. Twist 3 strands together clockwise again into a cord. Each direction reversal locks the previous layer's geometry. At cord diameter, a properly executed 3-strand counter-twist structure in ichu grass or comparable bast fiber achieves working load limits of 80 to 120 pounds in a 6 millimeter diameter cord, equivalent to a commercial nylon utility rope of the same diameter. Scale to a 25 millimeter diameter 3-strand cable using the same progressive method and working load exceeds 2,000 pounds. The QS Huachaca primary cables at 200 millimeters diameter carry loads measured in tons. The plant material available to you without purchasing anything depends on your climate, but the list is longer than you expect. In temperate North America, stinging nettle stems, dogbane stems, cattail leaves, iris leaves, and basswood inner bark all yield bast fibers of adequate tensile strength for cordage production. In the American Southwest and Mexico, agave leaves, yucca leaves, Imin and soto leaves provide fibers used in cordage production for at least 8,000 years based on archaeological evidence from Danger Cave, Utah. In Europe, nettle, flax, and hemp provide the historical bast fiber base. In tropical regions, banana plant pseudostem fiber, coconut husk coir, and sisal agave all yield cordage-grade fiber. You are not looking for a specific plant. You are looking for long, parallel-aligned cellulose fibers in any plant stem, leaf margin, or inner bark, and that description covers dozens of species in every inhabited climate on Earth. Harvest your plant material at the end of the growing season when fiber content is highest and moisture content is lowest. For most bast fiber plants, this is late summer to early autumn. For grass species including ichu equivalents, harvest after the seed heads have dried and the blade has gone from green to pale yellow. I cut stems cleanly at the base with a sharp blade. Crushing the stem base damages the fiber alignment and reduces usable length. For bast fiber plants such as nettle or dogbane, wet the harvested stems by submerging them in slow-moving water for 3 to 7 days. This process allows bacterial action to break down the non-fibrous plant tissue surrounding the bast fibers without damaging the fibers themselves. After retting, scrape the stem surfaces clean with a flat edge. Separate the bast fiber bundles from the woody core by bending the stem sharply and pulling the fiber away from the breakpoint, and spread the separated fibers in a single layer in full sun for 24 to 48 hours until completely dry. Fiber that is not fully dried before cordage production will shrink as it dries in finished cordage, reducing twist angle consistency and lowering working load by up to 30%. Esta for steps 4 through 6. Begin the twist process with a bundle of parallel-aligned fibers approximately the diameter of a pencil, held between the thumb and forefinger of your left hand at the midpoint. With your right thumb and forefinger, twist the right half of the bundle clockwise, no ichu, away from you at the top, until it begins to kink. Fold the kinked right half over the left half and allow the natural counter torque in the twisted section to begin twisting the two halves together. Continue alternating. Twist the upper strand clockwise, fold it over the lower, advance the working point forward, maintaining consistent twist angle throughout. This is the reverse wrap method, identical to the technique documented in Inca cordage samples and in every traditional fiber culture on Earth that independently developed twisted cordage. To join additional fiber as your bundle runs short, overlap new fiber with the existing bundle end by at least 10 centimeters before continuing the twist. The friction generated by the helical geometry locks the new fiber in place without knots. Finish the cord end by tapering the fiber bundle over the last 5 centimeters of length, twisting it to a fine point that will not unravel under tension. The Queswashaka bridge load testing data from the 2019 Rensselaer survey found that the primary cables, rebuilt from fresh ichu grass in the annual community ceremony the previous year, sustained static loads of 3.2 tons across the full bridge span without measurable deformation. A load equivalent to 12 adult humans plus equipment standing simultaneously on the bridge deck. Fiber samples taken from the cables during the same survey and tested at the Rensselaer Materials Laboratory returned tensile strength values of 480 to 520 megapascals, within the range of structural mild steel wire and above the tensile strength of standard aluminium alloy cable. The FAO's survey of traditional plant fiber cordage across 34 traditional cultures, published in 2018, found that properly prepared and twisted bast fiber cordage achieved working load limits within 15% of equivalent diameter commercial nylon rope in every sample tested, with the additional advantages of zero UV degradation, zero microplastic shedding, zero petroleum dependency, and full biodegradability at end of life. A 100-foot roll of quarter-inch nylon utility rope costs between $12 and $20 at any hardware retailer and has a working life of 2 to 5 years before UV degradation reduces it below safe working load. A 100-foot length of hand-twisted nettle or dogbane cordage of equivalent diameter costs nothing beyond the 4 to 6 hours of processing and twisting time required to produce it, has a working life equivalent to nylon under comparable conditions, and can be produced anywhere those plants grow, which is everywhere in the temperate northern hemisphere. The Inca did not budget for cordage. They harvested it, processed it, and built the most technically sophisticated suspension bridges in the pre-Columbian world with it, and the last of those bridges is still standing, still load-bearing, and still rebuilt annually by the community that has maintained it for 500 unbroken years. Every roll of synthetic rope on every hardware store shelf right now exists at the end of a supply chain that begins at an oil refinery, passes through a petrochemical plant, a plastics extruder, a packaging facility, a distribution warehouse, and a retail logistics network. 6 links, any one of which can break. And when they break, the alternative is not nothing. It is the ground beneath your feet. Either you can produce a structural cordage material from the plants growing within walking distance of where you are standing right now, or you cannot. The Inca made that capability universal across an empire of 12 million people and used it to build infrastructure that outlasted the empire itself by 5 centuries. Learn the reverse wrap this weekend with whatever plant material you can find. Share this with someone who has never considered that the most critical survival material in their kit grows wild in the field behind their house.